This episode is brought to you by Wold Anvil. Ancient alchemists dreamed of turning lead into gold, potentially creating tons of it, massive riches, but here on SFIA we would say that lacks ambition. Why settle for tons of gold when you can make whole planets out of it? So today's topic, nuclear transmutation, is continuing our informal trilogy on useful things you can do with nuclear explosions that we began back in January with our look at the Orion Project, a spaceship propelled by nuclear bombs, and then with nuclear terraforming, seeing how bombs could be used to make places like Mars or Venus habitable to humanity. It's weird to think of nuclear weapons as useful tools, but just as anything might be used as a weapon, any weapon tends to be useful in some other fashion too. As it says in Isaiah, they shall beat their swords into plowshares and their spears into pruning hooks. And while the usual post-Cold War notion is to dismantle nukes to use the fissile material for power generation, or maybe to keep some back for emergency use against an asteroid or alien mothership, the notion here is more that you might start mass producing them for peaceful ends instead. If you're new to the show, welcome to SFIA, where nuclear bombs get the overdue praise they deserve, and we regularly talk about devices that make them look like mere firecrackers. And don't forget you're drinking a snack, we will be here for a bit. Now while we will be talking about how a nuclear bomb might make cool new elements, our main focus today is really more on the entire concept of nuclear transmutation, how it happens in nature and how we can do it artificially and potentially make materials rarely found in nature. Or for that matter, simply not found in nature at all, such as the transuranic elements, those elements heavier than uranium but so short-lived they are not found naturally, many measuring their lives in tiny fractions of a second. Indeed, virtually all elemental isotopes would consider a second-long lifespan generous compared to what they got. We will also be contemplating the topic of the Island of Stability, the hypothetical region of super-heavy elements that are not short-lived, as well as some exotic materials like stuff made out of strange quarks, and we'll throw in some discussion of using black holes and neutron stars to forge materials, as well as building things out of them, proton decay, iron stars, and why iron is so critical in the discussion of nuclear alchemy. And that last might be a good place to begin, because iron is essentially part of the problem. To the best of our knowledge, the universe began as a small hot soup that cooled into a lot of dark matter, of which we still understand little, and a little bit of stuff made of up and down quarks and electrons. This little bit of stuff is what we call regular matter, and most of it is protons by mass. A distant second by mass is neutrons, and far behind in mass but roughly equal to protons in number are electrons. Protons, like neutrons, are made of up and down quarks, which are only two of the 6 known quark types, and the proton's antiparticle is strangely rare, as is the positron, the electron's antiparticle. The two bigger cousins of the electron, the muon and tau particle, are also pretty rare and they're antiparticles too. So most of the universe was dark matter, and we are pretty sure dark matter is not made of those other types of quarks, incidentally, though it has been considered, and can't yet be ruled out either. While most of the universe was dark matter, a decent bit of it was protons, and much of those paired up with electrons to form basic hydrogen, with a decent bit more pairing with one neutron and electron to form deuterium, or 2 protons, 2 neutrons, and 2 electrons to form helium, and a lot is ionized and floating around, occasionally getting an electron partner and losing it again. This plus dark matter made up very nearly everything in the universe when it began, and this is mostly still the case, but the misconception is that a lot of stars formed, burned out, went supernova, and gave us everything heavier than helium. This is not really true though. First, most of the stars that ever formed since the universe began are still alive and kicking. Only bigger ones have died thus far, and even then most of the dead stars weren't big enough to go supernova, they are just larger than our own sun, which is bigger than 95% of other stars itself. The bigger the star, the shorter the lifespan. Of those stars that died and didn't go supernova, most just turned into red giants then blew a lot of their outer layers off, which included some elements besides hydrogen and helium, then contracted into white dwarfs. Sometimes these semi-dead stars absorb a fresh intake of new hydrogen, often acquired from a binary neighbor, and turn into a nova, which also releases some interesting new elements. Very occasionally, this kind of explosion will be very big, a Type 1a supernova, and unlike Type 2, the giant exploding stars, these supernovae produce a very tight range of energy when they happen, and thus make really good distance markers for other galaxies, by comparing how bright we perceive it to be to how bright it would be expected to be at its origin and calculating the distance. Like if you knew a candle flame seen at a distance was a certain brightness, and thus you could tell how far away it was, hence why we call Type 1a supernova standard candles for measuring distances to ancient galaxies far, far away. A big chunk of the iron in our universe comes from these old white dwarfs reigniting and exploding, as do many other materials. Additionally, after a supernova you get a neutron star left behind, usually a very hot and fast spinning one we call a pulsar. Very rarely you will get a black hole formed from this, and in both cases these Type 2 supernovae produce a ton of stuff heavier than helium, but often these big stars are binaries too, and either they eat their neighbor and explode, or their neighbor dies and becomes a remnant white dwarf or neutron star too. They can also collide, and those explosions also produce a lot of elements we have, and indeed most of what we have that's heavier than iron. Iron, what's the big deal here? Well, the simple answer is that fusion in stars is always about trying to cram ever more protons and neutrons into a single nucleus, as those require less energy or glue to hold them together per particle, and the more it takes to tear it apart. Protons and neutrons are collectively called nucleons, and initially the more of them you pack into a nuclei, the more stable it is with less energy binding it together. Energy which can be released outside the nuclei as heat, what drives stars to be hot and radiant, and what we hope will one day power fusion reactors here on Earth. However, once you get to about 50 to 70 nucleons, stability peaks out and generally starts to drop as you add more. Now, there are many combinations of protons and neutrons in this range, some of which are not even vaguely stable, like iron 50, which like all iron atoms has 26 protons, but only 24 neutrons in this case, for a total of 50, and it only lasts an eye blink. Literally, it has a half-life of just 150 milliseconds. This is still longer than most possible isotopes, which are so hard to make and short-lived once made that we don't have them all cataloged. An important term when discussing the subject is isotope. It simply means a specific number of protons and neutrons for a given element. For example, I just mentioned iron 50. 50 is the number of nucleons, and the iron part tells you that 26 of those nucleons are protons, as is the 26th element on the periodic table, and the remaining 24 nucleons are the number of neutrons in that isotope. Now, that 150 millisecond half-life I mentioned is actually fairly long-lived compared to many isotopes we'll discuss today, and as mentioned is longer than many of the possible combinations of protons and neutrons that would add up to 50 to 70, but the most stable one with 26 protons is iron 56, which is about 92% of all iron we find in our ore samples. Nickel 62, which is actually rather rare, has the highest binding energy per nucleon of any known nuclide, just a little higher than iron 56, but just doesn't form as much in these stellar engines. As a result, iron 56 and other elements with very high binding energies per nucleon are basically an in-state for fusion. They poison the process because any further fusion will require more energy in than out, and that's what causes that explosion, or rather implosion. No fusion occurring anymore in a stellar core results in a rapid collapse of that core, followed by detonation. Now, during that explosion we have astronomical amounts of energy released, and some of it gets absorbed by elements in that explosion. It doesn't matter if these absorptions are net positive energy states. Think of a wave hitting a seawall. In the impact, some water will be given enough energy to send it much higher than the rest of the crest of the wave, even when most of the water remains below crest height. Folks on the other side of the wall get splashed, and this is how heavier elements are created, ones that don't provide an energy advantage when fusing. As a result, they are generally created far less frequently in the universe than those on the smaller side of iron. The thing is, the heavier those atoms are, the more nucleons per atom. Once we get past this stable plateau of iron 56 and a few cousins, the more unstable those atoms tend to be, such that nothing heavier than uranium-238 sticks around for very long in stellar and galactic terms, and there are precious few combinations of protons and neutrons between iron and uranium that stay stable for long either, usually only a few for each element, or specific number of protons, even though there's dozens of possible numbers of neutrons any given number of protons might be shoved together with. This is called the Valley of Stability, and it's a highly upward curving river on a map of protons versus neutrons in an atom. That river is an increasingly wide and bumpy one though, full of lots of borders of instability. Generally, the more nucleons you try to cram together, the more of them need to be neutrons too. For instance, most of the oxygen we breathe is 8 protons and 8 neutrons, but oxygen with 9 or 10 neutrons is stable too, if rare, oxygen 17 and 18. Similarly, most of the carbon in us is 6 protons and 6 neutrons, carbon 12. But carbon 14, 6 protons and 8 neutrons, is not stable but lasts thousands of years, making it great for dating objects by measuring the decay of carbon 14 in them, as it's created by events in our atmosphere. Stars are not the only places where atomic alchemy occurs. Down in this range you can have semi-stable isotopes with fewer neutrons than protons too. Carbon-11 has a half-life of 20 minutes, nitrogen-13 is 10 minutes, oxygen-15 is about 2 minutes, and helium-3, 2 protons and 1 neutron, is stable, as is single-proton hydrogen. Calcium-40 is the last known stable isotope with an equal number of protons and neutrons, at 20 protons and neutrons, and it has 26 known isotopes, ranging from calcium-35, with a half-life of 26 milliseconds, to calcium-60, and 5 of those, calcium-40, 42, 43, 44, and 46, are thought to be stable, with calcium-41, 45, and 47 having half-lives of days or years, and everything else in minutes or fractions of seconds. After calcium, nothing is stable without more neutrons than protons, and by the time you get up to uranium-238, the most stable uranium atom, and the last we think of as naturally occurring, we have 90 protons and 148 neutrons, 64% more neutrons than protons. Though plutonium-244, with 94 protons and fully 150 neutrons, probably should count as natural, as it does have a half-life of 81 million years, and it can be found in nature on Earth, albeit in trace amounts. We traditionally refer to every element bigger than uranium as transuranic and consider that synonymous with artificial elements usually only found in a lab, but some argue we should be saying transplutonian, and I recall someone saying that Pluto, Lord of the Underworld, was doubly snubbed for this and having his namesake planet demoted. In any event, there's 80 elements with some known stable nuclide, a few with more than one for a total of 252 nuclides that are not known to decay. Tin incidentally has the most, 10 stable nuclides, and 26 of those 80 only have one stable nuclide, being called monoisotopic. Technetium, 43 protons, and promethium, 61 protons, are the only elements until you get up to lead, 82 protons, with no stable isotopes. And lead-208 is the last known stable isotope. There are also just under 1,000 known isotopes that are at least metastable, defined as a half-life of more than an hour, and some like uranium-238 last billions of years. Emphasis on known because there are many combinations that might exist and just don't get made much in nature. We tend to assume with some justification that stuff which is most stable not only persists longest but tends to be synthesized easiest, but that may only be a loose trend, and again nickel-62 is more stable than iron-56 and everything else, but way less common. Incidentally, you will hear the terms nuclide and isotope used pretty interchangeably, but isotope is always talking about the same element, same number of protons but varying neutrons, uranium-238 and uranium-235 for instance, whereas while those are nuclides too, neptunium-238 or protactinium-235 would be other nuclides. More unstable versions of either are called radionuclides or radioisotopes as they emit radiation when decaying, and are pretty critical to nuclear energy. This is also where the notion of the island of stability comes in, because while we have made atoms in the lab all the way up to 118 protons, an atomic number of 118, There is some reason to think that valley of stability that ends at the Big Lead Dam might see itself re-emerge down the line. Incidentally, the atomic number element 118, called oganesson after the physicist who helped discover it, with 294 nucleons in it, was first synthesized in 2002, and only 5 or 6 atoms of it have ever been made, and it has a half-life of about a millisecond. It itself has no particularly interesting properties of those we have been able to observe or estimate thus far. It's not super strong or thought to be a superconductor or ultra-awesome spaceship fuel. The island of stability is a notion that's been kicked around for about a century now, practically since we figured out what protons and neutrons were, and that atoms had nuclei, and we didn't have anything but uranium, and before we even successfully synthesized the first transradic elements in the 1940s. So the concept has undergone a lot of variations and speculations, scientific and science fiction, from fairly hard sci-fi to comic book soft to the point of being as hand-wavy as magic, what we usually call clock tech if we discuss it seriously at all. Technologies so advanced they are indistinguishable from magic. It probably does not help that most of it revolves around what are called magic numbers, the number of nucleons needed to completely fill a given shell as you make a nucleus bigger. Those are 2, 8, 20, 28, 50, 82, and 126, with 184 being the next predicted one at the time, but 126 was later repredicted as maybe being 114 instead in the 1960s by the same two physicists who appear to have coined the term island of stability. Anyway, for protons, those magic numbers would correspond to helium at 2, oxygen at 8, calcium at 20, nickel at 28, tin at 50, and lead at 82. I've mentioned all of those thus far today as being significant. Helium and oxygen, for instance, are the two most abundant elements after hydrogen itself. Calcium, the last stable one, with equal protons and neutrons. Nickel-62 has the highest binding energy per nucleon of any known nuclide. Tin has the most stable isotopes at 10, and lead is the last known stable element. So the assumption was that anything that has the next magic number in protons, be it 126 or 114, might be stable, or less unstable than their neighbors, and the same for one with 184 protons. Now we also have the notion of doubly magic atoms, which are those who have what is termed a magic number of protons and also of neutrons. Helium-4, oxygen-16, and calcium-40 would be examples of that, having 2 or 8 or 20 of each. But calcium-48, 20 protons, and 28 neutrons also would count and is indeed stable, or very nearly, with a current estimated lifetime of nearly 1 billion times the age of the universe, which is pretty impressive for such an imbalance of neutrons to protons so low in atomic number, 28 to 20. Lead-208 is also a doubly magic number, 82 protons and 126 neutrons, and again lead is the heaviest known stable element, and lead-208 its heaviest of 4 stable isotopes, making it the heaviest known stable isotope. That said, a few of the other doubly magic nuclides have half-lives of less than a second, and we can make element 114 now, albeit not 126, and have not observed any special stability to it. 154 is another possible magic number that might offer an island of stability, and folks sometimes suggest we might have a whole continent of stability above 300 nucleons, and we are up to 294 these days, so we might get to see that tested sooner rather than later. I don't want to dip any further into why these are thought to be stable. It is not just numerology though, there are various models that hint at it, but there's no special reason to think they would have awesome properties if we did make them. No reason not to either. Odds are good any stable element is going to have some handy uses, though mass producing them would generally be necessary, trillions of atoms of them, not 1 or 2. We'll get to methods for doing that shortly. Now as a reminder, things do not magically die after their half-life. It is a time in which a sample of them will have half decayed into something else, and if you come back after twice that time it will be cut in half again rather than all being gone. Whether by decay or by being hit by something else, like a neutron, many nuclei then become some other nuclide, many of which are not stable either, indeed often not as stable as what they decayed from, things upon the higher sides of that valley of stability waiting to roll down. This is essentially how we get energy from nuclear fission or radioisotope generators by instigating such a change via fission or waiting for a passive decay. Stuff can happen real quick at this scale though, and sometimes these decay products can cause other decays in a chain reaction, and that's a nuclear fission bomb. One of our problems with whacking things with neutrons or alpha particles or so on is that we really can't do a lot of this. We absolutely can make gold by bombarding the next lower elements with neutrons, it's just that the next lowest atom happens to be platinum, and the process of that particular bit of alchemy is way more expensive than either is worth. At the moment anyway. The next biggest atom after gold is mercury, which is in second place to tin for having the most number of stable isotopes, whereas gold only has the one, gold 197. Platinum has 5 stable isotopes itself, one being platinum 196, which if you add a neutron to becomes platinum 197, which beta decays into gold 197 after about a day. So not hard to do with a neutron source, and platinum 196 is about a quarter of natural platinum isotopes, but platinum is generally about as valuable as gold, so it's not seen as really useful like turning lead into gold would be, especially as neutrons are a pain to generate and aim. A neutron bomb, a fusion bomb set off in space basically, wrapped in a wide thin shell of platinum 196, big enough not to be ripped apart by the fusion device, would produce a lot of gold. And I should point out that gold does not come principally from supernovae, rather the current theory is that we get it from neutron-star collisions, which are hardly super common, and of course neither is gold. It is possible to make gold from lead or even bismuth, which is both naturally occurring and a decay product of the thorium-uranium fuel cycle. Usually though, this is where someone points out that it would just never be profitable because of how much energy it takes. This of course is why nuclear bombs are potentially useful, because they are fast, cheap energy and neutrons. Regardless, the problem with discussing nuclear transmutation, be it by nuke or supercollider, is that it is assuming you are short on energy, which is fair as our own civilization is definitely energy poor and raw materials rich. In a genuine nuclear economy, especially a fusion one, or a quasi-fusion one like space-based solar power dialed up to onto the Kardashev scale, this completely breaks down. I want a pound of material, and I need to pay 1% of its mass energy equals mc squared to transmute it from something more abundant. That seems absurd in modern context because a 1 kilogram conversion would be running us about a quadrillion joules of energy, a petajoule, about 16 Hiroshima A-bombs worth of energy release, or enough fuel to fill up 160 Boeing 747s, roughly $20 million in jet fuel. However, it is also the amount of energy incident on a square solar panel 150 meters or 500 feet on a side up in space above our atmosphere over the course of just 1 year, which mind you could just be a shiny sheet of aluminum foil that big bouncing that light into a more compact power converter. And now we're talking about a few $1,000s worth of aluminum foil able to convert a kilogram a year of something, and looking at the spot price for gold today, it is $57,000 a kilogram. And of course the other thing about aluminum, a material ridiculously abundant on Earth, the Moon, and many other places, is that almost all its cost is electricity or energy for separating it from ore, making it even cheaper in an energy-rich society. So we picture folks going to mine asteroids for platinum and gold and other rare elements, but they might do that a different way, mine it for abundant aluminum and silicon and such, for building giant energy farms and huge colliders, and making the stuff from other abundant feedstocks. Phosphorus comes to mind since it's pretty rare, as we looked at in our Fermi Paradox episode on phosphorus scarcity, and is thought to be made in supernova from silicon. We do not need to replicate a supernova, we just need to whack silicon with neutrons. That's not our only alchemical option either, we can pound on things with alpha particles, helium atoms without their electrons, which are very easy to make and move electromagnetically, and through gamma or beta bombardments. Potentially all that combinations, patterns, and energies of our choosing, maybe even beams instead of big undirected explosions, like a particle laser. Lasers, particularly X-ray and gamma-ray lasers, can be useful in such alchemy too, if we can ever make them or feel comfortable employing one-time use nuclear bomb-pumped lasers, If you have a lot of energy and not a lot of material, cost gets relative. We can mine the asteroids, we can outright disassemble moons and planets, we can even drink matter off our own sun via star lifting. We can also go fetch it from around or in other stars, and there will be a cost for each of these options based on the various technologies and abundances. In the end though, if you need a gajillion tons of something rare, or which does not even occur in nature, you need to go make it. And possibly sustain it too. We often discuss using active support as an alternative for super strong materials, basically where you hold something up electromagnetically or by shoving out mechanically or with a light beam, and there may be materials that can only exist under extreme conditions, much as many minerals can only form in the nightmares of heat and pressure found deep underground. Neutron stars and the neutronium they are thought to be made of, essentially one big clump of neutrons, is such an example, held together by the immense force of gravity. We may find some materials can be fabricated and forced to remain together by artificial and careful use of the other known physical forces. We may also find out how to make artificial gravity. Nor should we rule out that we might figure out ways to play with the basic physical constants of the universe. This might let you start doing weird things like making matter out of other quarks besides up and down, the strange charmed top and bottom quarks, or with muons in the place of electrons, or even making particles which do not naturally exist period, like an electron with twice its normal mass. That's definitely in the Clark-Tech zone of things. Alternatively, as huge as they sound, physically or conceptually, building a giant supercollider around the sun, fueled by the sun's light, and sucking particles off the sun for refining and transmutation is merely unbelievable in scale, not physics. The science involved is pretty simple and old school, and it is probably faster and cheaper to convert locally abundant materials into scarcer elemental neighbors this way than to go mine them from around distant stars, where you either need to spend mass energy levels of energy to get them here in decades, or wait millennia for slow and cheap shipments. And eventually you would need to move further afield to find those and wait longer and pay more. So for Dyson building civilizations, this is probably something they eventually need to contemplate, which is what we usually expect civilizations to turn into. Dyson swarms around stars, Kardashev 2 civilizations, be they classically biological like us or something synthetic, iron or silicon based, not carbon. If you need X amount of material Y per person, and you got a lot of excess of something else you can make into Y, then you need to get or make X more of that to make another person or keep them alive or in comfort. Odds are, that's what you are going to do. Now, if these are galaxy-wide problems of shortages, you might opt for something potentially grander and more efficient, like running a beam of matter at ultra-high speed, skimming real close to a neutron star or black hole to let gravity do your crunching for you, or use them as abundant source of gamma rays for bombardment of nuclei. There are some potentially dangerous ways to suck the matter off a neutron star cheaply, relatively speaking, by having it in close binary with another one, but that strikes me as a really good way to accidentally end up with a merger or detonation, also known as a supernova. To be fair, that will get you plenty of heavier than iron elements, if it happens. It is one of the principal ways to get made, after all. Now, folks often talk about harvesting natural supernovae for heavy elements, and folks often talk about how nuclear bombs, the fusion kind anyway, are like the power of the sun. But it bears mentioning that H-bombs are not very sun-like at all. Our sun is a very slow converter of hydrogen into helium. Our attempts at controlled fusion are not about replicating the conditions in our sun's core, because that produces very little energy gram for gram. Indeed, it takes 5,000 kilograms of solar matter to generate a single watt of energy. It's just that it will generate that single watt for billions of years. Indeed, even the ultra-fast burning supergiants are generally only produced in the watt per kilogram range. H-bombs are way better. They convert matter to energy in mere instants, and with ratio parallel to supernovae rather than supergiants, let alone our sun, which itself is on the fast and high-powered side of things as stars go, most being cool and slow-burning red dwarfs. I want to emphasize that supernova point because we can make H-bombs of any size we want. They scale up pretty well, and doing that trick where you surround them with some big material shell that is to be transmuted makes a lot more sense in terms of time, energy, and safety than waiting on a supernova, or intentionally inducing one through ion poisoning or some of the other tricks we looked at in Killing Stars. Indeed, given that we talk about using nukes with pusher plates for running spaceships, this might be a trick used for metal production. Plate the back of your ship's pusher with a material you want to transmute, and fire your nukes off, scrape the valuable layer off, and repeat, all the while gaining the normal benefit of ship propulsion too. I could imagine some automated extrasolar mining operation bringing back feedstock for transmutation and using their ship's drive to allow that transmutation en route. For that matter, one problem with ships needing to run on radioisotopes is running out of the material partway through the journey because the half-life of that element was shorter than the trip was, and a transmuting pusher plate might be an alternative for some materials, especially ones you didn't need till you were nearing your destination, like radioisotopes for powering small probes or communication satellites for your early colonial efforts. One final note on all of this. I mentioned earlier one non-stable element that still had a half-life millions of times longer than the current age of the universe, and there's quite a few in that zone. Indeed, we don't really know for sure that any element is totally stable, and it has long been hypothesized that protons might decay given long enough. Neutrons do in mere minutes left to themselves. The proton decay number is way longer, usually more than a trillion years. If protons do not decay, we tend to assume slow quantum effects would transmute every dead bit of matter not in a black hole into iron, what we call iron stars, so far into the future that time can only be usefully discussed in scientific notation. And maybe they should be called iron 56 stars because the assumption is that by quantum randomness, fusion and fission decay are slowly shifting everything to this ultra-stable isotope. But we do contemplate civilizations lasting that long, trillions of years, and long beyond. See our Civilizations at the End of Time series for more on those. And these folks might need to be worrying about seemingly stable materials decaying on them, or replacing things with half-lives so long we today would think of them as near eternal, but those civilizations at the end of time would think of them as short-term and as spoilable as we do bananas. Indeed, as we point out in our episodes discussing freezing people for long interstellar journeys, just the tiny amount of potassium-40 in bananas and other foods, the modestly rare isotope of potassium, half-life 1.25 billion years, that decays into calcium-40, will eventually give a frozen human lethal radiation poisoning if they are frozen for a few thousand years, killed by the trace amounts of that potassium isotope in their own bones and tissues. Personally, I would not be surprised if in the future we started centrifuging radioisotopes out of anything we were using to grow food or clothes for people. It would be very energy intensive to centrifuge potassium to use only stable isotopes of it in hydroponics or house construction, but cost is relative, especially in energy abundant post-scarcity societies, and this sort of nuclear alchemy might be very much on their minds if they find their post-scarce situation is being endangered by a critical shortage of some element. So civilizations might very well turn to killing stars or mimicking their death throes to run themselves, if they needed to, or using nukes for elemental alchemical production. It just depends on how explosive the rise in demand is. So we've got quite a few announcements today along with our upcoming schedule, but first, while I was working on today's video, I kept thinking of Alchemy and Transmutation, and it reminded me of various characters in RPGs I've played down the years who specialized in those occupations, and who varied from Jekyll and Hyde style characters to those pursuing coveted alchemical secrets. If our episode comments and social media forums are any indicator, then an awful lot of our audience has played their fair share of D&D and similar games. I've been gaming for over a quarter of a century now, and playing in or designing all those worlds has been some of the best and most stimulating fun of my life. Over the years, and as it's transitioned from strictly pen and paper to the modern digital age, our options for connecting with other folks to play with has only risen, as have tools for forging new worlds to set your games and stories in, and the unrivaled leader of the pack when it comes to world-building tools is World Anvil. World Anvil, the award-winning world-building toolset, has tons of tools for enhancing your game or building your setting, It is intuitive to learn and has a giant stockpile of free tutorial videos that not only show how to use those tools, but suggest ways to improve your world building in general, to make it easy, appealing, and informative to your players or audiences. Whether you're managing a campaign or writing a novel, whether you're making city or dungeon maps, or connecting them to each other and a wider world map, or crafting family genealogies for your heroes, villains, and NPCs, World Anvil lets you forge your setting better and easier than anything I've ever worked with before. And it has a free version so you can share it with others, and selectively so they're not seeing secret content and spoiling the game. And you can also incorporate ways to monetize your content, such as Patreon or Ko-fi or your own storefront. World Anvil gives you the tools to build and share your dreams and tales with others. World Anvil offers Wikipedia-like articles for your world setting, interactive maps, timelines, an RPG manager, and a full novel writing software. All the tools you'll need to run your RPG campaign or write your novel, and never lose your notes again. If you would like to give World Anvil a try and let it help you forge new worlds, just click the link in this episode's description. For anyone who still wants to register, I'll be giving closing remarks for the conference on the future of space cooperation between the US and Japan on March 7th and 8th, hosted by the RAND Corporation. And there's going to be some great speakers there, starting with David Kipping from Cowords and Peter Warden, the director of the Breakthrough Starshot Initiative. I'll attach a link for the event and registration to see it in person or online in the episode description. I will be getting back home just in time to release next week's episode, The Million Year Machine, so apologies in advance if there's a delay releasing that, or if I'm less active in the comments of the video. I mentioned last week that the conference will be my first in-person talk I've given since COVID hit, and I will also be giving the keynote for the Bioscene conference on biomimicry, and in addition will finally be speaking at the National Space Society's International Space Development Conference this year. I had been scheduled to give a talk and accept my 2020 Pioneer Award from them right before the pandemic hit, so it is nice to finally get to do that talk. Those are both open to the public too, but will be in May, so we'll give details and updates in a month or so. It has been a pretty crazy last couple years with COVID, they seemed a lot longer. Ironically, the nearly 8 years since our first episode sometimes seems like just yesterday, and it is a good reminder just how short such times are compared to even most of the short-term projects we discuss on this show. Next week we will be examining those longer projects, many of which will need to encapsulate a million years or more to accomplish, in our episode The Million Year Machine. Then we'll have our March Sci-Fi Sunday episode to look at the concept of synthetic life, and we'll keep to that sci-fi theme as we return to our Alien Civilization series to contemplate the concept of clandestine extraterrestrial operations and covert aliens. And after that, we'll jump forward to the distant future and look at a time when the moon has become an enormous mega city. Now, if you want alerts when those and other episodes come out, make sure to subscribe to the channel and hit the notifications bell. And if you enjoyed this episode, please hit the like button and share it with others, and leave a comment below. You can also join the conversation on any of our social media forums, find our audio-only versions of the show, or donate to support future episodes, and all those options and more are listed in links in the episode description. Until next time, thanks for watching and have a great week.